Moodle wanted them. Well, the way I set up Moodle to grade them automatically, I went through and regraded, so that should all be up to date as of this morning. Uh, Mainly went okay. The biggest problem or the biggest mistake that I saw consistently was on the second problem where I gave you a function and asked you to find the vertical asymptotes. A lot of people factored the bottom correctly and got where the bottom was equal to 0, but didn't check to see if there was a common factor in the top. Remember, if you reduce it to lowest terms, then everything cancels on the bottom, and there's just a hole there and not a vertical asymptote. So that was the big one that was a consistent mistake over and over again, but mainly they were pretty good. So I just want to make sure I mentioned that before we get started. Are there any other questions at all before we start your stuff? Yeah, Jasmine.
I was wondering if we could kind of start going through number 4 on the website.
On the website, sure. Log in real quick. See if I can get to that real quick. On 3.7?
Yes.
Okay. That's not what I wanted to click on. That's what I wanted to click on. Well, assuming it loads. There we go. 3.7. Oops, I hit the wrong one. There we go. Number, that one?
Yes.
Okay. So we've got, yes, okay. So we got x minus 5 over, and I'd be changing different numbers from what you've got because it randomly does it. Greater than or equal to 1. So anytime that you have anything that has a polynomial inequality or a rational inequality, first thing we need to do is get 0 on one side. So we need to make sure that we subtract over the 1. And the reason for that is our big technique is, there's a piece of chalk up here that's not broken to shards. Our big technique is to factor everything, right? So the next step here is to get everything as a single fraction. So what do I need to do to get everything as a single fraction in this case? Yeah, make the denominators the same. So I'll multiply the second one by the 2x plus 9. And then minus, or that was equal to 1. We have that. Running out of room, so I'm just going to mute the projector for the time being. So what do we get now when we combine those two things? Well, the denominator is definitely what? 2x plus 9. What's the numerator going to be? Yeah, it'd be minus 14 because I got to distribute that minus sign all the way through. That's exactly right. Yep. And now we'll attack it like we've done all the rest of them. So when's the top equal to 0? Negative 14, good. And the bottom? So that'll make our number line. Negative 14 is smaller than negative 9/2. And then we'll pick our test points. So if we pick something like negative 15, that makes the top positive but the bottom negative. This is negative 4.5, so maybe negative 5. The top will be negative, but the bottom will be positive. Or sorry, yeah. Try that again. That's right. Negative and negative. Sorry, the whole thing will be positive. And then if you put it in 0, you'll get negative. this case, we're looking for the greater than, so we're looking for the positives. So the interval will have the lower bound is, or the lower endpoint is negative 14. The upper endpoint is negative 9 halves. Now you figure we need brackets or parentheses, right? So the equal to tells us we probably need parentheses for some of them, but I have to be careful. If it makes the denominator equal to 0, we don't use a parenthesis. So for the left-hand endpoint here, do we use a bracket or a parenthesis? Bracket, because that's the top is equal to 0. And the other one is parentheses, yep. Yeah, that makes sense? Okay. Other questions? We're good? All right, well, let's start some new stuff. Close all that stuff here. Put that back opened up. So we're going to switch gears. We're going to introduce new types of functions in this particular chapter. We're going to introduce exponential functions today. And then we're going to talk about logarithmic functions next week. Pardon me. So logarithmic functions are the inverses of exponentials. So really we're going to start with exponentials and then undo exponentials, essentially is what we're going to do. So let's talk about what we mean by an exponential function. Well, before I write down the definition, you can see in that example that I have listed, I've got a new type of function here where I've got a number in the base and a variable up in the exponent, right? Okay, that's different than what we've dealt with before. For polynomials, the variable is in the base and the exponent is a number, right? So it's reversed. So when we talk about an exponential function with base a, so we say that this function has the form, if f of x is equal to a to the x. So again, the base of the expression is a number. The variable is up in the exponent. So when you put in numbers in for x, you're changing the exponent, not the base. Okay. Now we do want to make sure that this a has a special property. First off, we want a to be positive. The reason why we don't want a to be negative, all right, you don't have to write this down. I'll write it off to the side. The reason why we don't want a to be negative is if, say you had f of x is equal to negative 1 to the x, and I asked you what is f of a half, what does a 1/2 exponent tell you to do? It's a square root. Yeah, remember the denominator of a fraction in an exponent tells you what root to take? Right? And now I have square root of negative 1. I've got a negative under my radical, which is going to make that a complex number. But what we're dealing with are what are referred to as real valued functions, meaning the answers that you get out of your function should have to be a real number, not a complex number. So negative 1 wouldn't be in the domain. Okay? We want our outputs to be real numbers, not complex numbers. So whenever we have negatives for our base, we get all sorts of domain issues. Okay? We can't do 1/2, we can't do 1/4, can't do any even fractioned exponent. Okay. So that's why we want to make sure our base is positive. The other case that we want to get rid of is we don't want a to be 1. Not because it can't be 1, but what happens if a is 1? What do you get all the time when you plug something in for x if your base is 1? What do you get all the time? 1, right? Because 1 to any power is 1, right? So you always get 1. That's not very interesting. You already know what that looks like. It's a constant. The graph would be a horizontal line.
Joe,
Yes.
is there another copy of it for her? She got
Oh, yeah. Anybody else need one who came in late? All right, so when we have an exponential function, again, our base is a constant, exponent is the variable. We want to ensure our base is not negative, and we also want that we throw out the case where the base is 1 because that's not interesting. All right, so the first example here just wants us to sketch a graph. We don't really know much about these functions so far, so our best way of sketching a graph is to just plug in some numbers for x and get out some numbers for f of x. So let's just pick some. Maybe we do -3, -2, -1, 0, 1, 2, 3. See what happens. When we put in -3 into the function, we get 2 to the -3rd. What does a negative exponent tell you to do? Does it mean make the number negative? Is that what a negative exponent means? No. What does it mean? I think you're thinking about the right idea, but not quite there. What does it tell you? Yeah, so yeah, it's a division thing, right? Take the reciprocal, right? The negative tells you to do 1 over that. So this is the same thing as 1 over 2 cubed, which gives you an 1/8. So what do you get when you put in -2? You get 1 over 4, right? You get 2 to the -2, which will be a 4th. The next one will be 2 to the -1 will be a half. Good. 2 to the 0 power will be 1. And then 2 to the first is 2. 2 squared is 4. 2 cubed is 8. So if we plot these, at -3, we're at 1/8. At -2, we're at 1/4. -1, we're at 1/2. 0, we're at 1. 1, we're at 2. 2, we're at 4. 3, we're at 8. Those are what the dots look like. And if we play to connect the dots, we go from low to kind of go up and to the right. Do we ever cross the x-axis? Does this ever hit the x-axis? No. Because again, a negative exponent says flip it upside down, right? When we flip it upside down, we'll have a 1 in our numerator. That's never equal to 0. Right? However, the bigger negative number that you plug in, the smaller it's going to get, right? You're going to do 1 over 2 to the 4th, 1 over 2 to the 10th, 1 over 2 to the 20th, right? You're going to get really, really tiny. So we're going to get really, really close to the x-axis and then go up into the right this way. So that's what that graph would look like. And what we're going to do later on here is collect some important information about exponential functions. Notice this shape. We've got a horizontal asymptote here at the x-axis. Right? We get really, really close to that line, just like our rational functions. We talked about the horizontal asymptote, same concept here. But this one in particular goes up and to the right, and we crossed the y-axis at 1. That's okay? So let's look at the next example, where we do 1/3 to the x. Let's do the same idea. Let's make a table of values. I'll put in -2. I won't put as many points in this time. I'll do -2, -1, 0, 1, and 2. What do you get when you put -2 into the function in this case? What does the negative exponent tell you to do? Use the reciprocal, so this becomes 3 squared, right? What do you get? 9. When you put in -1, you get 3. When we put in 0, we get anything to the 0 power is 1. Yeah, good. There you go. Actually, I lied a little bit. 0 to the 0 power is undefined, but anything else to the 0 power is 1. When we put in a 1, we get a third, and we put in 2, we get 1/9. Good. Yep, exactly right. So we plot these points. We put in -2, we got 9. -1, we got 3. 0, we got 1. 1/3, 1/9. Again, is there anything I can plug into this function and get 0 out? Is this ever going to cross the x-axis? No. I can't raise a number to a power and get 0. Right? I can never get 0 out. So again, we're going to get really, really close to the x-axis. In this case, it's going to go this way and go like that. Again, we're going to collect some properties. Notice in this case, we didn't go up to the right. We're going down to the right, right? Looked around. But there are some other similar properties. Still have a horizontal asymptote of y = 0, the x-axis. Still crosses the y-axis at 1. Still has a y-intercept of 1. And also notice, if I go back up to this one and compare it with the other one, this one's going up all the time. This one's going down all the time. But notice that it passes the horizontal line test. Right? If I take a horizontal line, it only intersects in one point. That told us something about inverses. And I already alluded to the fact that we're going to talk about the inverses of these functions next week. So these all these functions have inverses as well. Any questions on how we got those graphs? The graphs okay? Okay. All right. So, pardon me. Let's talk about some properties. The domain. So again, let me write down just the form of the function again. It was a to the x. We're going to refer to that here in a minute. Again, remember your a is positive and cannot be equal to 1. Was there anything that we cannot plug in for x? Or are we allowed to put anything we want in for x? Anything, right? So what's the domain going to be? -infinity to infinity. Good. Okay. No holes in it at all, right? No holes at all, right? Okay. What about the range? What do we notice about both of the graphs? What are they always above? Yeah, they're always above the x-axis, right? So your y's are going from what to what? 0 to infinity. Do we hit 0? No. So we'll have the open, the parenthesis on 0 to infinity. And that was true in both the examples we did, right? Both examples, we had a range of 0 to infinity. Again, how do we find a y-intercept for a function? Yeah, plug in 0 for x. Anything to the 0 power is 1, so the y-intercept is going to be 1. Yeah, the 0.01, right? For all exponential functions, doesn't matter. They're always going to have that property. What about horizontal asymptote? Excuse me, horizontal. Try that again. X-intercepts. I was looking at the next line. X-intercepts. Did it ever cross the x-axis? No. So no x-intercepts. How about a horizontal asymptote? Do we see one of those? Yeah, it's the x-axis, so it's going to be not x equal to 0, but y equals 0, right? Because it's a horizontal line. Yep. So y equals 0, or the x-axis. Notice I haven't said anything about the particular function, right? This is these 5 things that we did. Every single exponential function has those 5 properties. Doesn't matter what the a value is. The next 2, pardon me, matters what the a value is. Okay, so let's go back up. I'm going to scroll back up to the pictures. Notice in this case we graphed 2 to the x. Would you say that function is increasing or decreasing? Increasing, right? Because it's going, as x gets bigger, the y gets bigger. That's what we mean by increasing, right? As you read from left to right, the function goes up. Right? So notice the base was 2 in that case, and we got it going increasing. What about this one? Decreasing, right? And the base was 1/3 in this case. So remember way back at the beginning I said your a value couldn't be 1? Your 1 is kind of a dividing line, if you will. Okay? If your base is bigger than 1, then the bigger the exponent gets, the bigger the number you're going to get out, right? For example, if your base is 3, when I square it, I get 9. When I cube it, I get 27, and so on. But if I had something like a base as a 4th, the bigger my exponent gets, the smaller the output gets. Because if I square a 4th, I get a 16. If I cube a 4th, I get a 64. Okay? The 1 is kind of the dividing line. So as far as the function goes, it's increasing if a is bigger than 1, and it's decreasing if a is between 0 and 1. And so this is where that first difference pops up in the difference in the exponential is based on the base. If the base is bigger than 1, it goes up and to the right. If the base is less, between 0 and 1, it goes down and to the right. Good news is that they basically have all the same basic shapes, depending on what they look like. So the reason why I did 2 to the x and 1/3 of the x is because they're examples of these basic shapes. If your a is greater than 1, it crosses at 1, still crosses the y-axis at 1, and again it goes up and to the right. So it has this basic shape. So we approach that horizontal asymptote as you go out to the left, but not the right. If you're between 0 and 1, still have that y-intercept, still have a horizontal asymptote, except that it comes this way. And those are the basic shapes. So if you know what the basic shapes are to start with, you can do some analysis of what happens as x gets big in the positive direction or x gets big in the negative direction, depending on what you're looking at. So for example, if you're interested in application types of things, this would be an example of an exponential growth kind of thing. Yes. If you put a negative out in front, yes, it can flip over the x-axis. Absolutely, yeah. We can still do the same transformations, and we'll see a couple of examples of that here. But not a dumb question at all. Very good question. Yeah. So we'll see some applications later on, but this kind of example is, well, as x gets bigger, this gets bigger really fast. We call that exponential growth. So that has applications to population dynamics. It has applications to compound interest. Lots of different applications for exponential growth. This one, as x gets bigger, the outputs get smaller. We call that exponential decay. So that has applications to, say, carbon dating, for example, or signal strength decreasing, those kinds of things. Okay. So exponential decay pops up. So these ideas pop up later on in applications, which, like I said, we'll talk about those later. But any questions about these basic shapes? Well, this goes to Joshua's question about can we ever flip it? All right, so this one asks us to sketch a graph. So this is the same kind of idea that we talked about earlier when we did all the transformations of the graph. So this one we've got a negative of 2/5 to the x plus a 1. Looking at this, what do you think you might want to use as your base function, your base graph? Yeah, so exactly, the decreasing one, because our base function, the 2/5 to the x, right? So our base graph will be 2/5 to the x. Our base here is 2/5. That's less than 1, so we know it's going to be going down to the right. So we know it crosses at 1. And I'm not going to be perfect with my drawing here, but 2/5 is 0.4, so that's about there. When I do -1, I would get 5 halves. That's 2.5. That's about here. So you'll get something that goes this way. I only just plugged in a couple of points to help me with some guiding there to get my graph that looked a little bit better. Right? When we put in 1, we get 2/5. That's 0.4. When you put in -1, remember negative flips it upside down. I get 5 halves. 5 halves is 2.5. So 2.5. That okay for the base graph? All right. Looking at this as my base, what transformations do you see? What things do you see happening to that? Yep, we got a reflection and a up one. Yeah, we got to shift up, right? Okay. So for our transformations, we've got a reflection about the x-axis. And the second one, we've got a vertical shift up 1. So first, let's flip it. So when we flip it, the 1 goes down to -1. The 0.4 goes to -0.4. The 2.5 goes to -2.5. So we get, I missed my point. That's okay. I got to redraw it for that. That was step 1. Did that change your horizontal asymptote at all? No, it didn't change it at all, right? If this one doesn't have one, then if I shift this graph left or right, does that change your horizontal asymptote at all? No. Okay. However, the last step here is to shift it up 1. Does that change your horizontal asymptote? Yes. Yeah, everything gets moved up 1, right? So for our horizontal asymptote, it's going to move up 1 as well. So it's going to end up here at y = 1. And then everything gets shifted up 1. So this goes here, this goes here, this goes here, and you get the final graph of that one. And it helps to shift those asymptotes, because remember the asymptotes are kind of guiding lines for your graph, right? Those are the lines you want to get close to. So keeping track of where those shift is helpful. You only really have to worry about it when you actually shift up or down. It won't do it when you stretch, as long as you do your stretches first. It won't shift, it won't move when you stretch it. It doesn't move when you reflect it. It doesn't move when you do a horizontal shift. It only moves when you do a vertical shift. What questions do you have on that one? Is that okay? All right. Let's look at the next one here. And this might be the last example. Work on this one for a minute, and we'll chat about it. I think we're going to have time to go on to a specific type of exponential functions. I'll go ahead and hand out those two. no, the homework for this won't be due until Tuesday. Next Tuesday. Thanks. That's my finger. Ready to talk about it? What'd you identify for your base graph? 3 to the x. I agree with that. Everybody okay with that? All right, we got 3 to a power, right? We got 3 to the x minus 2. So our base graph here should be 3 to the x. So is that going to go up or down? Up. Good. So the base is greater than 1. Good. What transformations do you see?
Down to
Now I say down to, which negative 2 is a down to?
the last one.
Yeah, the last, this is a down 2, right? What about the other minus 2?
That's a right 2.
That's a right 2, right? Because it's on the inside of the function. For exponential functions, this is your inside. That's where the input goes, right? So that's a horizontal transformation, okay? So we've got to shift right 2 units and a shift down 2 units. Okay, so again, this is the right, this is the down. It looks a little bit different, right? But the inside of an exponential function is the exponent. Okay? The inside of the exponential function is an exponent. So when you see that plus or minus in there, up in the exponent, that's going to be a left or a right shift. That makes sense? All right, so let's see if we can put these things together. You said our base graph was 3 to the x. So certainly if you put in 0, you get 1. 1, you get 3. 2, you get 9. So your base graph should be that one. We want to shift right 2 units. So here, 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 here. Again, when we shift right, that does not shift your asymptote at all. However, when we shift down 2, that does change your asymptote. So our asymptote originally is y equals 0. We shift it down 2 to y equals 2. Then I can shift these other points down 2 as well. And finally draw my final graph here. What questions do you have on that? That makes sense, what we're doing? Notice the transformation stuff is the exact same transformation stuff we were doing before, right? Just with a new type of shape. All right. All right, so on that next sheet that I handed out, I know it's a short one. It's the next section's short. We have a specific kind of, or a specific exponential function that we refer to as the natural exponential function. And we talk a little bit about where this particular exponential function comes from, which is why I have this table set up. Notice that this is not, what I have set up here is not an exponential function, right? For an exponential function, the base has to be a constant. Is the base a constant in this expression? No. I have an n in there, right? So this is not an exponential function, but it kind of looks like an exponential function. Let's just analyze this for a second, and then we'll start plugging some numbers into our calculator. That's what this table's for. That thing I just pointed at, the 1 over n piece. As n gets really, 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 really large, what does 1 over n do? It gets really, really, really small, right? You're dividing by bigger and bigger and bigger numbers. You get smaller and smaller values. So the base is getting really, really, really close to 1, the bigger n gets, right? You agree with that? If you put in something like a million, you get 1 and 1 millionth. That's pretty close to 1, right? Okay. What did we just say a little bit ago? I raise 1 to any power, I get 1. Okay, cool. All right, but notice at the same time, that exponent's doing something, right? That exponent's getting bigger and bigger and bigger and bigger. Now, no matter what happens on the inside with the 1 over n, it's still going to be a tiny, tiny bit bigger than 1, right? So if I had an exponential function, if the base is bigger than 1, what does this graph look like? It goes up and to the right, doesn't it? So the bigger the exponent gets, the bigger the output gets, and it goes off to infinity, right? It's really, really big. But you just said that 1 to anything is always 1. But if it's just a little bit bigger than 1, it goes off to infinity, right? So we've got what we refer to in mathematics as what we call an indeterminate form. I cannot tell what's going on with this particular expression without doing some more work. Okay? 1 to any power is typically 1, but anything raised to the infinite power usually gets really, really big. So I don't know where I am as far as that goes. That's what we refer to as an indeterminate form. Okay? So let's play around with it a little bit. And that's all this table of values is doing, is playing around with this expression as n gets really, really big, right? I plug in 10, 100, 1,000, 10,000, and so on up the line. Okay. Well, if we put in 1, that's not hard to do. 1 over 1 is, plus 1 is, to the first power, 2. So it just comes out to be 2, right? Now we got to do a little bit of work. So that's 1 plus a tenth to the 10th power, or a tenth is 0.1, right? So I can write it as 1.1 to the 10th. Anybody type that into their calculator? (2.59-ish). Okay. Now do the same thing for 100. If you're able to edit your previous thing that you typed in, it's probably easier just to go grab it, insert a 0 in here, and add a 0 to your exponent. Make it a little bit faster to type it in. What do you get here? 2.7-ish. Okay. Is that what others are getting when they type it in? 2.7-ish. Do the next one. This will be 1.001 to the 1,000th. .72. Now notice these numbers are getting bigger, but are they getting bigger really fast? No. Okay. Do the next one. 1.0001 to the 1,000th, or the, oops, this should have been 1,000th. Sorry. To the 10,000th. About the same thing. Can you carry out a couple more decimal points? Yeah. Okay. Yeah. So they. Yeah. So the next one should be. We do the next ones. Let's see if I get this one here. 1.1234 to the 100,000th. This next one should be about 2.71827. And the next one should be, oops, I didn't put a extra zero in there. Well, I'm illustrating that this really is getting closer and closer to a specific number. That's why I want to do that. So this is 2.718280, I think it is. Okay. All right. So these numbers, they're getting bigger, but they're slowing down when they get to, right? So what happens is as n gets really, 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 really large, these numbers get really, really close to a special number that we refer to as e. Okay? So the natural exponential function is, we refer to this as f of x equals e to the x, where e is it's an irrational number, meaning it cannot be written as a fraction. Like pi is irrational, or square root of 2 is irrational. It's the irrational number that is approximately 2.7182. It actually looks like it starts to repeat, but after that point it doesn't repeat. So E is a number. It's a little bit less than 3. Just like pi is 3.141592, blah, 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 right? Pi is another number, close to 3, but a little bit bigger. E is kind of like pi in that respect. Okay? It's close to 3, just have to be a little bit less. But it's a number, okay? And it's the number that these values get close to. In math, we refer to that as a limit. It's the limit as n approaches infinity of that expression that we just did a minute ago. Oops. Not approximately, approaches. As n, all that means when we talk about taking a limit, it just means that we keep plugging in bigger and bigger and bigger and bigger and bigger and bigger values of n and see what happens. What happens is we get really, really close to that number e that we're talking about. All right, for our purposes, it's the base of an exponential function and it's bigger than 1, right? So it has the same properties as those exponential functions that have a base bigger than 1. So what's the domain? Good, negative infinity to infinity. Range is not quite 1. We look at the graphs. What do we get really, really close to?
0.
Yeah, 0, right? We get really, really close to the x-axis. Y-intercept. Where does it cross the y-axis? Anything to the 0 power is 1. Does it ever cross the x-axis? No. Horizontal asymptote. Y equals 0. Good. And since the base is bigger than 1, is this increasing or decreasing? Increasing. Good. So these are the important properties of e to the x. So again, its basic shape is going to go up and to the right and cross the y-axis at 1. That's what its basic shape is going to look like. So it looks like every other exponential function that has a base bigger than 1. The reason why we call it a natural exponential function is it comes out of that expression, which may not look exceptionally natural, except that if you've got a business slant, that's the compound interest formula. If you compound your interest twice a year, or 4 times a year, or 12 times a year, or so on, that's the compound interest formula. That's where it comes from. The more times you compound, you might think, hey, I'm going to get an infinite amount of money. Well, no, it doesn't work out that way. Okay. So anyway, we'll chat more about natural exponential function next time, as well as get into logarithmic functions. So everybody have a good break. If you're traveling, travel safely.